Let me ask you a question. What do these three images have in common? You might say that, well, it's very hard to see what's going on in them. The top ones are very dark and the bottom one is too oversaturated. Wouldn't it be nice if there existed a method to correct them? Well, there exist many methods, and one of them is called image or histogram equalization, which we will explore in this video. But in order for us to understand this algorithm, we first need to know a little bit about how images work and how they're represented in digital computers. Let's take a look at this image of a very normal looking cat. As we can see, it consists of a lot of different colors. However, when we take a closer look of the cat's eye and its nose, we can see that the entire image is actually made up of a lot of small colored squares. These are called pixels, and there are typically hundreds of thousands or even millions in an image. In computers, a pixel gets its color from a blend of three primary colors: red, green, and blue. Each of the three are represented by a value from 0 to 255, describing its intensity, where 0 is completely dark and 255 is very bright. From these three values alone, around 16 million color blends can be created, so there is no problem displaying colorful images on a computer. Notice if all values are 0, the pixel is black, and if all are 255, the pixel is white. Another way of describing images, as you probably know, is black and white, also called grayscale images, where the pixels are different shades of gray instead of colors. A way of converting the pixels in a color image into a grayscale is by using this formula here, where 0.299 is multiplied by the red value, 0.587 is multiplied by the green, and 0.114 is multiplied by the blue value. There exist other formulas like this, but they each have their benefits and downsides. We'll be using this one here. As you can see from the formula, the green value has a greater impact in making this shade of gray lighter. The smaller the number of the gray pixel, the darker it is, and the higher the number, the lighter it is. Let's take a random grayscale image like the one at the bottom here. We now know that the pixels each have a gray value from 0 to 255, describing how gray they are. So we can now count those and stack the ones with the same value on a graph. Each bar on the graph depicts the amount of pixels in the image with that exact gray value, and the bars are called bins. And this entire graph is called a histogram. We could also do the same with a color image, but because each pixel is made up of a blend between the three colors red, green, and blue, we therefore need three different histograms. Here we see a small histogram with only 4 bins. Each bin describes how many pixels there are in the image with that exact shade of gray. However, this can also be described in percentages. So here 50% of the pixels in this image are in the third bin of the histogram. This histogram with percentages is also called a probability mass function, PMF. But in this video, I will use the term for the continuous version instead, called a PDF. The cumulative distribution function, also known as a CDF, can be created from the PDF by summing up the percentages as I show here in the animation. We need both of these to understand the histogram equalization algorithm. To understand how the histogram equalization algorithm works, let's take a look at this dark image and its histogram, that is the PDF, and the corresponding CDF, which is marked by white dots. Most of the pixels are dark, so it makes sense that the first bins in the histogram, containing the darkest pixels, has the highest values. And the CDF reaches 100% almost immediately. But let's see what happens after we equalize the histogram. Well, the bins have been distributed equally over the entire histogram. This can also be seen by the linear CDF going from the bottom left to the top right. Let's look at another example. In this example, the image is not too dark, but the distribution of gray is just bad, and we want to equalize it. Using the same process as before, we get a nicer image. So how does the algorithm actually work, and how do we do this in practice? Well, luckily it's very easy, and I will explain it with an easy example. Here we have a grayscale image of a heart, which looks fine in itself, but for the purpose of explaining this algorithm, we will equalize it anyways. We see the histogram, that is the PDF, and the corresponding CDF of the image to the left. There are 7 scales of gray going from 0 to 6. Here at the bottom, we will be calculating the equalized histogram. First, we take the number of the last bin, which is 6 because the first bin is number 0. And then we take the number of the first bin in the CDF, which is 34%. Then we multiply them and round down to the nearest integer, which is 2 in this case. So that's it. Now we know that the bin 0 of the original image should be the bin number 2 in the equalized image. And we update the hard by changing the corresponding pixel values. Let's calculate for the next bin, the bin number 1. We again take the number 6 like before, and we multiply it by the CDF value of bin 1. We round down to the nearest integer, which in this case is 3, so bin number 1 in the original image should be bin number 3 in the equalized image. We can continue to do this for the remaining bins in the histogram, and notice how both bin 2 and 3 in the original histogram go to bin 5 in the equalized one. And now we're done. Since the image was fine to begin with, there is no real reason to equalize it, which is why it looks really weird. But hey, the CDF is now linear, so the algorithm was successful. So in the future, if you have an image that looks weird, then take a look at the histogram. And if the distribution of the bins is bad, then try equalizing it.